First of all, thank you so much for coming to the Space City Aeronautics Critical Design Review of 2025-2026 competition, DBF competition aircraft MV-1. So we are Space City Aeronautics. We are one of the two competitive teams under AIAA along with rocketry. Before we get started, here is the agenda of today's presentation. We're going to start with the team introductions, and then we're going to look into past DBF missions and our past entries, and DBF 2026 mission, and then we're going to look into mission requirements, mission challenge, scoring, criteria, and tech inspection. Next, we're going to go over our aircraft MV-1 overview, and then we're going to go over the schedule and budget. After that, you're going to hear about updates on from our each sub-team. Those are aerodynamics, structures, avionics, and our payload sub-team is banner systems this year, which is a capstone team. So starting with the team introduction, we have minor changes to the team members or project leads from the previous semester. First one being our systems engineer, Gabriel, has now graduated. So we no longer have a systems engineer. Our project leads are myself, project manager, my chief engineer, Francesco. Our sub-team leads, we have also minor additions. So Carson, he was chief engineer last year, and 2 years ago, he was the aerodynamics sub-team lead. He went to do his co-op, but now he's back. So he's back in aerodynamics team as a sub-team co-lead. So in aerodynamics, we have Carson, Rahul. Structures is not changed. We have Shane and Nathaniel. And in avionics, we have Nathan and Jake. Looking at our team structure, our faculty advisor is unchanged, Dr. Baksavanis. And we are, again, under AIAA acting as a parent organization. And myself, Emir, and Francesco, project manager and chief engineers. In aerodynamics, we have Rahul, Carson, avionics, Jake, Nathan, structures, Nathaniel, and Shane. And in banner systems, which is, again, a capstone team, we have myself, Nathaniel, Sean, and Max. One thing I want to mention here is Carson is also going to be our pilot for the competition and for the test flights. He has the previous experience of flying the Carbon Cougar, which is a plane from 2 years ago, and he has been training. So he will be our team pilot.
All right, so now let's talk a bit about the Design Build to Fly competition. So Design Build to Fly competition is an RC aircraft competition hosted by AIAA. The challenge changes each year. It includes 3 flight missions and 1 ground mission. At the end of last year, around September, we had to submit a proposal, and the top 100 proposals worldwide get invited to the fly-off. This year's fly-off will be in Wichita, Kansas on April 16th to 19th. Now, this year's competition is a theme under a banner towing bush plane, where we have to design, build, fly a banner towing bush plane that can also do shorter missions and deploy a banner. We do have some major constraints like a max wingspan of 5 feet with a minimum wingspan of 3 feet. We can only have a battery with a capacity of 100 watt-hours maximum. Due to FAA regulations, we cannot have a plane with a max takeoff weight of over 55 pounds. And each mission has a flight window of 5 minutes. The first mission is a simple mission of we just have to complete 3 laps flying the flight path with no cargo, with no banner, just regular standard flight configuration. And we have to do it under 5 minutes. We just have to do 3 laps, and after a successful landing, we get a score of 1. For our second mission is when we start the shorter section of the competition, where we have to complete as many laps as possible under the 5-minute constraint, carrying as many ducks and pucks as we can. There are some constraints, though, with this mission, which we have to have a minimum of 3 passengers, minimum of 1 cargo, and our minimum cargo to passenger ratio is a 1-to-3 ratio. We also must load all the cargo and passengers in a staging box under 5 minutes before flight happens. Now, our mission score is based over a 1 plus net income over the maximum net income someone has earned in the overall competition. The net income is based on the number of ducks and labs, minus the cost, which is also based on the number of ducks, bugs, and labs, but also multiplied by the amount, the total propulsion battery capacity. Our third mission is when we are doing the banner deployment, where after we do initial takeoff, we must deploy the banner after the first turn, do as many laps as possible under the 5-minute flight window, and then before landing, we must deploy the banner and have a successful landing. Now, some of the constraints are we have a minimum banner length of 10 inches with a minimum banner height of 2 inches. The length to height ratio is 5:1. And during flight, the banner must stay stable and vertical. Now, for the scoring, it's a scoring of 2 plus the laps we do times the banner length divided by the RAC score. The RAC score is based on our wingspan. So it's 0.05 times the wingspan plus 0.75. So it's giving us a constraint of trying to reduce the wingspan as much as possible. And then it's all divided by the maximum score someone got. Our last mission is the ground mission, which we must complete a set of tasks as fast as possible. The scoring is all based on time. We must load and unload all cargo and passengers. We must also install the banner, deploy the banner, and we also must verify that all control systems are working. And this will all happen in a box of 10 by 10 feet. When it came to our design methodology, we had a linear engineering-based path where we started with the conceptual design, looking at all constraints. We analyzed all the mission requirements. We then move over to a preliminary design, figure out the sizing we needed. We did some performance analysis, certain trait studies on all different components. We then move over to having a detailed design. We finalized a lot of details. Then we started manufacturing. Then afterwards, we move over to testing. We evaluate all the testing, how the design performed, and then depending on how we feel, we will on how the test comes out, we would either go back to the drawing board and fix the issues that come up, or finalize those designs for the final competition aircraft. Here's our design approach for each specific mission. For the first mission, we just got constraint of we needed proper maneuverability to fly the course. The aircraft had to fly at a certain velocity to ensure we fly the 3 laps under the 5-minute window. And we also needed to make sure that the plane was easy to manufacture. For our second mission, we wanted to maximize the amount of cargo space for the ducks and the pucks. We needed to maximize the amount of laps we could complete. We also had to make sure that our wing was capable of producing enough lift to make sure that to take off with all of that cargo. And we also had to make sure that the cargo and the passengers could be loaded under the 5-minute window. For our third mission, it was all about stability. We had to make sure that we had a stable flight. We had to balance our speed and efficiency on aerodynamic efficiency, but we also had to minimize our wingspan. Now, for the ground mission, it is all about, it ties up with mission 2 since they both have to do with ease of cargo loading, but also included the banner loading system had to also be quick to engage. Now, before we could even fly, we do have to pass tech inspection. Tech inspection issues verifying the safety of the design, ensuring that everything is good and flight ready. We must have a signed pre-tech and first flight certification form. We must show a video of straight and level flight. None of our batteries can exceed 100 watt-hours. If we have multiple banners for the mission 3, they must all be brought to tech inspection and signed off. And then we must also verify that we have a fail-safe mode, which is having the throttle closed, the full up elevator, full right rudder, full right aileron, and full flaps down.
Okay. I would like to now talk about the team goals that we set for ourselves beginning of this year. We had 3 major goals. Those were attending competition fly-off. Again, it comes from our proposal scoring being in top 100 proposals overall. Second one, manufacturing a flying prototype by CDR. Third one is actually attending competition and attempting all 3 flight missions and 1 ground mission. So looking at those goals right now, we have successfully achieved the first goal, which is attending combination fly-off. Our proposal scored 17th out of 175 teams globally. Also scored the best in Texas, which is the best score for in the team history. Looking at the second goal, design and manufacture a flying prototype by CDR. As you can see, our prototype plane is here. In terms of flying prototype, it is currently missing minor things, monocoque being one of them, and the battery and ESC, like avionics installation on the aircraft. But besides that, the plane is there. And we are hoping to achieve our last goal in April at the competition. Now going over our aircraft configuration and overall layout, MV-1. These major configurations are not changed since PDR. So we are currently looking at a monoplane, high wing, conventional empennage and fuselage aircraft, also integrated fuselage, so no tail boom, single tractor propulsion system, single motor battery, tricycle landing gear with a wingspan of 51 inches and a wing core length of 15 inches, and a dual decker payload bay given the payload constraints of or challenge of this year's DBF mission. Looking at our Gantt chart, this is the Gantt chart that we created to start of the project. So far, we have completed conceptual design, preliminary design, detailed prototype 1 design. We have worked on prototype 1 manufacturing, and we expect to complete that within a week. And we are currently working on some of the early testing and validations that we proposed. However, I would like to mention here that we are indeed about 3 weeks behind of the Gantt charts that we proposed because of few issues. Main one being no access to a manufacturing lab space. So we were expecting to start building the plane over the winter break, given our lab building or lab space at TechBridge. But unfortunately, that did not happen, and our backup plan was created at UH Makerspace in the Bates Law, and we had to wait about 2 weeks for that to open when the semester started. So we have that kind of setback in our Gantt chart. But looking at our remaining weeks and going forward schedule, so week 1, starting next week, we are hoping to implement feedback from CDR and start designing the MV-1 aircraft, which is, let me make this clear, MV-0 prototype aircraft, MV-1 will be the final aircraft, final competition aircraft. In week 2, we hope to start the test flights of MV-0 aircraft, our prototype, and start early manufacturing of the final aircraft, MV-1, starting with the laser cutting. In weeks 3 and 4, we are hoping to manufacture the aircraft, which final competition aircraft, which includes the assembly of the parts, gluing the parts, electronics assembly, and 3D printing the necessary components. And 4th week will then include the final monocoque wrapping of the aircraft. And 5th week will be the final flight tests. And subsequent week, we are hoping to attend the competition April 16th through 19th in Wichita, Kansas. So looking at the team budget we have, first of all, this year the project is sponsored by the floor, which the floor funding will be used for the electronics, structural, and manufacturing cost of this aircraft, but also manufacturing tools in the for the future years. In avionics and structures they are covered by floor funding, and when we look at the detailed budget, we are looking at about $450 for avionics and $443, so almost very similar for avionics and structures, with the main components being the motor, propeller, carbon fiber rods and spars, and monocoque wrapping, which only includes the components that we purchased this year And it is worth noting that we are reusing some of the parts from previous year's aircraft. When it comes to logistics, they are not covered by floor funding. We don't plan to do that. And we are looking at about $425 for the fuel, which we are planning to take 3 student cars from Houston to Wichita, Kansas. We are expecting $1,216 for lodging, which we secured already via RBO. And for the food estimates, we are looking at around $530, which is for 10 people and for 5 days, which then brings our total project cost to be $3,614. And again, this is total project cost. With the floor funding accounted, is it going to be about $2,171. After we subtract our current funds, which is not floor funds, our existing funds, we are looking at around $1,187 as for the funding gap. With that being said, I will give it to Aerodynamics for their updates.
Hey guys, my name's Rahul. I'm the sub-team lead for Aerodynamics.
Hey, I'm Carson. Good evening. I'm one of the co-leads for Aerodynamics.
So what do we do in Aerodynamics? We design, manufacture, and analyze the wings, empennage, and their associated control surfaces, as well as any other aerodynamic related components of the aircraft. So there's really 2 components to what we do, the analytical components and the structural components. The analytical being the airfoil, wing and tail configuration, lift analysis, stability analysis. Then we move on to the more structural components, which is the actual design of the wings, empennage, and control surfaces. Softwares we use include XFLR 5, COMSOL, MATLAB, and CAD software. So from basically going from PDR to our first prototype, that's basically conceptual design to physical prototype. So that being said, what got updated was the empennage sizing itself. We took into account volume coefficients this time. In the past, we would just use rules of thumb that we had in the back of our heads. Now we take into consideration the wingspan, the surface area of the wing, as well as moment arms. So those associated formulas are displayed, and from doing said calculations, we determined that the span should be 27 for the horizontal, a mean chord of 8.45, aspect ratio of 3.27, and taper of 0.57. And vertical would be 78.03 inches and span of 11 inches, mean chord of 7.19, aspect ratio 1.57, and taper of 0.55. Just more about the horizontal stabilizer. The diagram on the bottom left corner was the rules of thumb we used in the past. They weren't terribly inaccurate. However, the new formulas allow us to take into account the wings, surface area, and wingspan as said before. Same thing with vertical rules of thumb displayed here, and it allows for the same kind of considerations to be taken into account for a more optimized stabilizer. Control surfaces for specifically MV-0, the aileron, we will have ailerons, elevators, and a rudder. The aileron will be 5 inches of the chord, and then 10 inches of the span. Elevator is 5 inches of the chord and 100% of the span. Same thing with the rudder, it's 5 inches of chord and 100% of the span. The reason we did that specifically for the empennage control surfaces is to maximize our control authority. And updates on the stability analysis. So far, we've gotten 4 longitudinal modes and 4 lateral modes. However, we're still learning how to understand said data. The The results should give us static and dynamic stability data, and we will verify that further with Flow 5 and ANSYS. Based on our current data, the aircraft should go back to natural stability on its own after experiencing a disturbance.
So as far as center of gravity, this is one of our main aerodynamics issues that we have with the MV-0 prototype. So more of a casual test that we did gave a value of about 4 inches aft of the spar for center of gravity. So just over the fuselage a little bit there. That will change a little bit, but as far as flying goes, we're definitely not going to even try a test flight until we get the CG where we want. So as you can see there in yellow, that's basically kind of where it was. And then the green there is the acceptable range that we want for CG. As far as for our XFLR 5 analyses, we wanted to use the closest to the spar, so where it would be basically the most unstable. When I came in here in the spring, I wasn't obviously here for the main theory stuff in the fall, but for the spring, I wanted to do the team. We wanted to research a little bit. We wanted to research the winglet and also the idea of adding fairing to the landing gear. Excuse me, the landing gear. Obviously, neither are critical for the safety of flight, but definitely looked into for purposes of efficiency. So I did the winglet trade study here. As you can see, there's 4 different ones we compared: the traditional, blended, the end plate, and the Horner tip. We also compared it with no winglet just to make sure, just to compare the differences that we were getting. So the traditional winglet actually ended up winning. Before, we had kind of a holistic decision matrix, which included like integrity and manufacturability as one of the criteria, but really we didn't have a value for those. So we kind of took those out because really manufacturing is pretty similar for all of them and not as much of a concern. So we ended up just using the coefficient of lift, coefficient of drag ratios, the lift force and the drag force, which of course traditional won in 2 out of the 3 of those. And so yeah, that's what we're going to do for winglets for MV-1. For MV-0, we don't plan on testing the winglets. Landing gear fairing design. This was actually done by one of our members. I just did the CFD on it and got the drag force. So as you can see, the wheel alone has about 0.593 newtons, and then with the fairing, it reduces it to 0.578. So a little bit of a reduction, and that's on our 4.3 inch diameter wheel. There's going to be, of course, 3 on the airplane. So just a little, and again, another research item that we did.
So the final design parameters of the wings and the empennage for MV-0 include the following. The wing will have a airfoil of SD7032. It's a high wing configuration. The span is 51 inches and port being 15. The taper ratio, it's a constant forward and no sweep. The horizontal and vertical will both have a airfoil of NACA 0012, the span being 27 for horizontal and vertical being 11. And then taper ratio of 0.57 and 0.55 respectively, with also no sweep. Next, moving on, would be the aerodynamics MV-0 testing, which is basically center of gravity test. So the objective of the center of gravity test is to verify the actual CG compared to the analysis data. How we do that, the methodology would be a balance point test using a carbon fiber spar, and the expected outcome is that the ideal CG is forward of the wings.
All right, concluding for aerodynamics, we're going to talk about the lessons learned and the things we plan to change for the MV-1. So starting off, doesn't say it on here, but we actually made the control surface, the empennage, so the horizontal stabilizer in the tail, much bigger compared to last year, because that's actually one of the main factors of the mishap crash at DBF. Sorry, not last year, 2 years ago. DBF 2024 was the That was one of the main causes. So we are confident in our sizing for this year. As far as for MV-0, we're using again that SD7032 airfoil. One of the weaknesses of it, it does have some sacrificed lift generation compared to, for example, NACA 5412, which is what we used last year and the year before. So it, of course, the reason we used it was for efficiency optimization. We are sacrificing some lift. And so because of that, we are going to have to fly at a higher speed than, for example, with the 5412. We're going to have less lift. So we're going to have to fly faster, cruise speed, stuff like that. And of course, that could be a problem. Again, we talk about like landing, takeoff speeds, the landing gear. That's where the high takeoff landing speeds could be a problem. Of course, the main one is the CG. Again, we're not even going to do a test flight until we're confident that the CG is where it should be. For MV-1, we definitely want to give more frequent updates to structures as far as the CG calculation, so they know when they're finding their design where wing structures should be placed. And worst comes to worst, if we can't get the CG where we want it, we do plan to include ballast on the form of, as long as it can be secured, for example, in the forward part of the airplane, just to move that CG where we want it. That is always a backup option that we do have. Of course, it will add weight to the airplane overall. And yep, that is it for aerodynamics.
Good evening, everyone. I am Shane. I am one of the structure sub-team lead or sub-team co-leads.
I am Nathaniel. I'm the other sub-team co-lead structures.
So as a structures overview, we are responsible for the design, testing, and building of this year two aircraft. We again, for both those aircraft, will be designing, designing and testing, along with manufacturing, fuselage, wings, empennage, and the landing gear of these aircraft. Additionally, due to this year's mission requirements, we will also be having a payload integration added to our task list. So from PDR to MV-0, so our conceptual design that some of you may have seen from PDR to our physical prototype of MV-0. As far as our fuselage structure, there are some things that will change and some things that are unchanged. For unchanged items, we are still using an integrated fuselage design with no carbon fiber tail boom used. The laser cut components are still laser cut with the jigsaw design using frame ribs and bulkheads, again with the side plates. This is all going to be covered in a monocot style skin as to be expected for our team needs. For MV-0, we are changing some things. We're using less bulkheads, moving the wings about 2 inches back. We are hopefully we are going to be reducing weight by skeletonizing the cross pattern, reduced weight by skeletonizing the cross patterns and change the tail structure to a flat structure for easier integration of the empennage and horizontal stabilizers.
So the fuselage is a 2-deck fuselage. The top deck has the cargo in the front, and which is the pucks, and then the passengers are in the back on the top side. And in the bottom, in the front, is the avionics, and in the back will be the banner deployment system, and then in the back of the plane is the banner release system.
For our wing structure, we're going to use a similar construction to our fuselage body, that being laser cut wooden components with longerons and ribs. However, with our wings, we are going to be using 2 carbon fiber components, a 20mm square tube spar and a 1/4-inch rod, a carbon fiber rod reinforcement piece. This is again all going to be covered in a monocot style skin, and as aerodynamics mentioned previously, using the SD7032 airfoil profile. The horizontal stabilizer structure is very similar. However, there are a few distinct changes. So this again, the same construction as the wings with a laser cut basswood, a monocot style wrap. Again, that's the jigsaw with the longerons and the ribs. Our root core rib, which is going to be at our ends, and our root closest to the fuselage are going to be 3/8 inch thick. They were 3D printed with GCF or carbon fiber filament. There are 2 carbon fiber spars being used, one 10mm square main spar and a 6mm carbon fiber rod, which is also doubling as our control surface hinge axis. These is going to be using the NACA 0012 airfoil profile, again, as aerodynamics mentioned earlier. Our vertical stabilizer is also much the same. It is a jigsaw laser cut construction, monocot style wrap, This was also using 10mm square main spars and a 6mm carbon fiber rod, also again acting as the axis of rotation and still using the NACA 0012 airfoil. Our control surface systems. So our control surface system includes our physical control surfaces and our servo brackets. Again, avionics will go into further detail about the actual electronics. However, for structures, it's important to know that our ailerons are using monocot taped to the ribs as their hinge and are constructed using PETG carbon fiber as a filament. Our elevators are also using PETG carbon fiber as a filament, and again using the 6mm carbon fiber rod. Our rudder is going to be just standard PETG with no carbon fiber added, and also using the 6mm carbon fiber rod as our axis of rotation. Our servo brackets, which is these part in the small or in the bottom right, is our servo brackets, and they are also constructed out of PETG CF and fixing the servo with 3mm bolts and nylon locks.
So there's two main types of payload. It's the ducts and then there's pucks. So the graph on there is our sensitivity analysis that we made for that mission. And the darker red means the more points we get. And we have, with calculations, we have found out that 14 ducts and 4 pucks gives us the best score. So this is the duct holder design. It accommodates all different types of the ducts because there's a variety of them. It has Velcro on the bottom of the holders, and they Velcro right down to the base plate of the top side of the fuselage. And then there's also the puck holder. It also has Velcro on the top side, and there's also going to be Velcro on the bottom side. We have that here, yeah. And there's also going to be Velcro on the bottom side of this plate. The pucks are a tight fit, and they fit right into the holder, and you slide them right in and Velcro them down and then cross. And then the top one will also be it'll fit right inside, and we'll put it inside, and it'll be right on it'll Velcro right on top of the other. It'll be once there's Velcro, it won't move.
For the landing gear, we're using a tricycle configuration, say single nose gear and 2 rear gear. Both of them, this is a big change, both of them are going to be COTS or commercial off the shelf. We needed a large ground clearance due to this year's team and mission requirements, so 12 inches of clearance for the propeller and the banner systems. Our front landing gear bracket is 3D printed with PLA Plus using 4 walls and 40% gyroid infill. Our back landing gear bracket is 3D printed as well, and is additionally going to be layered with 1/16 inch aluminum plating on top and bottom of the 3D printed bracket. Now you may ask, if some of you were here last year or last PDR, you would remember that we said we were going to manufacture the front landing gear in-house. So we learned something but we discovered that even with our channels available to us as University of Houston students, manufacturing in-house is still convoluted and time intensive for the rapid prototyping that is required, and rapid changes are also required for the team. So the structures team was noting their previous landing gear was significantly stiffer than expected. And so we decided to test it on the airframe to see how it would perform. And it satisfied all the specifications that we would have listed for the manufacture of a new gear, and significantly reduced the costs that we would have had for not that much of a sacrifice in performance.
So the final design parameters of the plane, the fuselage is actually 57 inches long, but with the motor, it's 61.35 inches. The width is of 6.5 inches. The height is 8 inches. We have a vertical moment tail arm of 33.65 inches and a horizontal moment tail arm of 34.65 inches. And here are the weights for each mission, which varies from 7 to 10 pounds. And here is the 3-point configuration, this drawing that we've made. The drawing on the right shows the different configurations for each mission. We move on to MV-0 testing. So the wing structure loading test, we're gonna determine if the wings can stand the weight of the whole plane by grabbing both ends of the wings and holding it up, propping it up. This should show that our wings can withstand the whole weight of the plane. For the wing spar, we're also doing wing spar loading test. We're going to do 2 cases. One where we fix the ends and apply weight in the middle of the spar And then we're also going to do a case where we fix the middle and apply weights to the ends of the spar.
For a landing gear impact test, our objective is to determine if our landing gear can survive our classic Carson rough landings. So our method is going to be to drop the plane at certain heights with an applied forward force, starting at 1 foot, then 2 feet, then 3 feet, and with success with the 3 foot drops, moving on to 5 feet. These are going to be with the plane just dropped forward. It's going to then be measuring the deflection that we use and also testing for structural integrity afterwards. Our nose structure test is going to determine if the nose structure is strong enough for the maximum thrust that's produced by the motor. So our method is going to be to pull the nose structure at the motor mount with our maximum thrust force that we're expected, utilizing a force gauge in tension configuration. We're also going to be applying torsional loads on the front fuselage to simulate the propeller effect in a nonlinear curving fashion. So our lessons learned are design considerations for MV-1. MV0 is heavier than the team is expected. The total weight, including ducts and pucks, projected to be around 4.45 kilograms, or about 10 pounds. This is based on actual and projected weights, and until flight tests are completed, it is difficult to tell if this is a satisfactory weight for our mission requirements as of now. Again, like we mentioned earlier, mission 1 is 8 pounds, and mission 2 is 10 pounds, mission 3 is 8.3 pounds. So it is a somewhat significant variety of weights.
So our CG location is far back, so our plane is a little tail heavy. We are planning to put weight in the front of the plane to offset it to make it an acceptable range. And then structural changes for MV-1, we are planning to move the wings back more by either 1 to 2 inches, and we're going to make the plane a little bit smaller and lighter. We're going to cut 2 inches from the passenger bay because we've noticed that we put a little more room than needed, and move the bulkhead forward 1 to 2 bulkheads.
That is
The dividing bulkhead that's right here. That's dividing both bays. And then we're also gonna cut the side panels and not be like a full electrical plane, but more where the wing structure is, and then add fuselage stringers on the sides to reduce the weight on the main 2 side plates.
And that is all we have for structures. Thank you. Now it's avionics. We will have questions at the end. Yes, thank you so much. Yes.
Hello, my name is Jake Rodriguez. I am one of the avionics subteam leads.
Hi, I'm Nathan Mishitsky. I'm the other avionics subteam lead.
So the main goals and requirements of the avionics subteam lead is that we provide power, we provide the control surfaces and the propulsion of the plane. We also try to find the optimal motor and propeller combination that could provide the most amount of thrust as efficiently as possible. We also ensure that the servos controlling the control surfaces can handle the loads being put upon them, and we also ensure that the plane is ready for tech inspection. So going on from what we did from PDR to the MV0 prototype.
So these are our final design parameters for MV0. For our motor, we have a Sunny Sky 5320 210 kV motor. For servos, we have 8 servos. We have 7 Darrell servos and 1 MG995 servo. For our receiver, we're using a Spectrum 8360T. For our ESC, we're using a Spectrum Avian 100 amp ESC. For our transmitter, we're using an NX8 20 channel DS-MX receiver, or sorry, transmitter. For our propulsion battery, we are using a Light 6S 4500 milliamp LiPo battery. For our fuse, we're using a competition required 100 amp fuse. And for our propeller, we're using a Falcon 20x8 carbon fiber propeller. This is also the final circuit diagram for MV0. We have our LiPo battery in the top left, powering our ESC, which allocates how much power goes to the motor. These are connected with a 100 amp fuse as per competition rules. In the middle, you see the receiver, which is powered by a switch, universal battery eliminator circuit, and 2S small battery system. The receiver gets signal from the transmitter, which sends it to the ESC, which helps the ESC allocate power to the motor. Our receiver also powers 8 servos, 7 Dural servos, 5 of those being for the control surfaces, 2 of those being for the banner system, and we have the MG995 servo controlling the landing gear because it has a higher torque.
So we're gonna start talking about like the testing that we're gonna be using for the prototype. So we found 5 different testing parameters that we wanted to focus on, which were full circuit testing, thrust testing, battery drain testing, transceiver range testing, and servo load testing.
For our first test that is already completed, we did a full circuit test. We made the circuit from the diagram into reality. How we did this was we wired all the components together and we verified all the functions worked correctly. If needed, we ensured compatibility between all components. We saw new connections we needed, and we also bought additional wiring if needed.
So the battery drain testing is to find the maximum flight time of the plane. The way we're going to do this is we're going to run the motor at cruising speed for about 2-minute intervals and check the battery voltage after each run. We're going to do this for about 10 minutes. And the expected outcome is to kind of verify what our expected flight time of the plane will be.
For our thrust test, we are going to find the maximum thrust of the Sunny Sky KV210 motor. We're going to apply a load cell we're going to put the motor onto a load cell, and we're going to determine the thrust of the motor at different throttle percentages. This is to verify that the thrust data for the KV10 will be enough, and if the KV10 does not produce enough thrust, we will buy a new motor or MV-1.
So the transceiver range test is to find the maximum range between the transmitter and the receiver. The way we're going to do this is that the pilot will be holding the transmitter and sending signal to the plane while it's on the ground, basically just servo controls, and just kind of stepping back. The expected outcome is kind of to make sure that the transmitter can still transmit data to the plane at different distances, and that was enough to meet the competition requirements of how far away the plane will from the pilot during the competition flight.
We're also going to do a servo strain test. This is to find the maximum load that the Darrell servo can handle. We're going to have Darrell pull on a load cell that has weights attached to it until Darrell fails. And this is to ensure that Darrell can handle the predicted loads on the banner systems and control surfaces.
So these are the lessons learned that we have found out throughout the development of the prototype and leading into MV-0. The first is motor issues. Due to a previously unnoticed change, the thrust inefficiency data was using the 3070 kV motor datasheet, but not the actual 210 kV motor. The change resulted in a lower maximum thrust due to a smaller maximum current amperage of the 210 kV motor. Thrust test will determine whether the 210 kV motor will be sufficient or if Aeronautics will need to purchase a new motor.
We also had UBEC and servo issues. So the old UBEC and switch system was overheating and causing a burning wire smell. So we were forced to buy a new switch and UBEC. For the Darrell servos, we bought them with the thought that they turn 180 degrees. However, due to our transmitter's lower pulse modulation width range, Darrell only turned about 90 degrees. So we had to fix this issue by buying range extenders for the servos.
The final thing was ESC issues. The ESC was modified in an unconventional manner, which caused some confounding errors. The first modification was that the throttle control cable, the ground cable was taken out instead of the power. This is a design requirement of the competition where the ESC cannot power the receiver itself. It has to be done through the UBEC, but we need signal and ground to be able to communicate to the motor itself. So the fix was basically just take out the power cable, plug in the ground cable back in. Everything functions perfectly fine after making that modification. And the final thing was that the throttle control and the programming cable was mislabeled, causing confusion on which cable was actually required to actually send throttle control to the motor. And now it's banner systems.
Now moving on to the banner systems. Again, this is a capsule team, and this is basically our payload team of this year. So our role is basically designing and implementation of all Mission 3 requirements. So our scope is defined by Mission 3 activities, which comes from the deployment, release, and towing system of the banner. The goals we set for the team is maximizing Mission 3 score through reliable and remote deployment of the banner, limiting the banner drag forces below 10 newtons, and enabling banner lengths greater than 25 inches. To give you a quick recap of what happened since the PDR, we first started the project with the preliminary wind tunnel tests done on different banners of the same, so different banners, different sizes of the same material and same material of different sizes to get an idea of the drag coefficient of the within the banners at the expected flight velocities. Once we had an idea of the order number for the drag coefficients, we then use an Excel optimization code to optimize the banner dimensions and limit the banner drag force below 10 newtons, which resulted in 18 by 90 inch banner. Next, we designed deployment, tow, and release mechanisms. And after that, we did more research into banner materials. The preliminary materials we tested in the wind tunnel were bed sheets, which is just lightweight polyester, batiste, and denim, which bed sheet material performed the best. Which after we did more research into other materials, and we identified ripstop nylon and ripstop polyester as two candidates. So moving on to the changes from PDR to MV0.
So based on the data and analysis we collected from semester 1, we created two 90 by 18 ripstop banners. One was a polyester and one was a nylon, like Amir was saying. You could see at the top the three-way swivel, which attaches to the tow line, which is made out of a 50-pound test braided line. And on the lead pole, the carbon fiber lead pole, we have a 50-gram weight, which acts as a counterbalance to preserve verticality during flight. So banner drag testing went largely the same as it did for the preliminary prototypes last semester. Where these new banners were mounted on a test stand and attached to a force gauge, and there was we ran multiple tests at varying representative airspeeds based on how fast we predict the aircraft will go. After each run, we would record the maximum drag outputted by the force gauge, and after every run, we compiled all the data, and the data showed us that it was highly linear in the scatter plot.
All right, so this is the data from the actual wind tunnel testing. On the left is the ripstop polyester, and on the right side is the ripstop nylon. Some highlighted points are the total drag caused at flight competition speeds. That's roughly 19 meters per second. We're aiming to cause under 10 newtons of drag at this speed. So the ripstop nylon performed just under that at 9.5 newtons, whereas the ripstop polyester was well above it at 14.7 newtons. We also have the R-squared on there to show how linear of a relationship it is. They're both very close to 1, meaning it is a highly linear relationship. This data right here is actually the theoretical data from the analysis we performed last semester compared to the actual experimental data we got this semester with the ripstop nylon. The orange line is that theoretical data. That's the one we got from last semester, and the blue is the lab data. So the banner actually performed better than we even anticipated in our analysis.
Okay, so here we have our deployment and release modules. On top, our deployment module is a rotating hooked arm. And the way it will work is mid-flight, when the pilot decides to deploy the banner, the fasteners that are holding the banner, they will be released by the arm as it rotates 180 degrees.
And this will allow the banner to unfurl and be towed behind the plane. The release module, which is a rack and pinion gear system, will be holding the banner in place with a ring on the rack. When this system is activated, the rack will move so that the ring can slip out and cause a clean release from of the banner from the plane.
All right, so as far as the banner deployment and release systems being integrated with the rest of the plane, we do have them both mounted in the MV-0. They're just fitted onto the fuselage and then epoxied together. So we printed out some mounts for each of the servos, and then we have the actual moving components as well. On the left side, you see the banner deployment system that is actually on the inside of the fuselage towards the back. The small holes at the bottom of the fuselage is where the straps will be going through, securing the banner under the fuselage. The banner release system is mounted on the back of the fuselage, entirely outside of the plane. When the servo activates, the pinion gear goes down, releasing the hoop, which is directly attached to the tow line, freeing the banner. Yeah, continuation. This is kind of an example of how that banner release system works. Currently, both of these systems are working in isolation, meaning that we move the servos, they have their full 180 degrees of freedom that we wanted. These straps are falling. We have not been able to test it with the banner itself yet. That'll be our next steps moving forward.
Okay, and just to sum up, our final banner prototype is a 90 by 18 nylon ripstop banner. The logos are heat transfer vinyl, and the tow lines are made out of a 50-pound test braided line with a 3-way swivel, and this will allow the banner to attach to the back of the plane. The lead pole at the front is a carbon fiber rod, and at the bottom, it is a 50-gram counterbalance weight for verticality.
Right. So after we complete all the manufacturing of the MV-0 prototype, we are going to move over to the flight testing.
So before going to flight testing, I want to talk a bit about the flight performance estimates that we've done using MATLAB script that we developed. So we are able to estimate values like the bank angle, turn radius, turn time, the competition lap time, and maximum laps that we are able to do. We are also able to optimize velocity values to achieve a preferred performance, as you can see right here. So on the plot on the left, it is the velocity versus we optimize for maximum laps to loop one lap time ratio, which is we want to obviously maximize our maximum laps, but also minimize the time it takes to do one lap. So this is the preferred approach for given a flight course. And for mission 1 configuration, meaning mission 1 aircraft weight, we are looking at around 19 to 20 meters per second, which is roughly 40 miles an hour optimized velocity. And for mission 2, we are looking at a slightly faster velocity, around 21 to 22 meters per second, which is closer to 50 miles an hour. With those estimates in mind, we then looked into calculation of all the parameters that I mentioned before. So we are again able to calculate max bank angle, which are estimating around 55 to 40 degrees, depending on, again, weight of the aircraft, velocity, which is optimized. Load factor of around 1.5 to 2 Gs, turn radius, time to do 180-degree turn, and other these parameters. So again, mission 1 configuration expected or optimized flight velocity is 45 miles an hour. Mission 2, it's a little faster, 52 miles an hour, and 42 miles an hour for mission 3, which was actually optimized using the Excel code, not MATLAB. to take into account of banner physics. So
now for our different flight test, our approach will be to have Carson, our pilot, fly the plane throughout all different tests. And our current site, our plant site, is the South Area Radio Control Society. However, due to some unexpected costs, the team is looking at other possible sites at the moment. So the first test we're going to complete is the ground test. We're going to make sure that we can complete all the ground test requirements. We're going to be timing ourselves, and we're going to be repeating this test multiple times throughout the entire process, ensuring that we are able to optimize our time and make sure that the all loading systems work optimally, and we can hope to be one of the faster teams in the competition. For our first flight test, it's going to be a simple takeoff and landing test. We are going to be using the Mission 1 configuration. We will have the pilot take off and land, just fly around, fly at low altitudes in case of needing to do emergency landing. For a few tests we're going to be doing is we're going to figure out measuring our takeoff distance and takeoff speed, ensuring they align with the calculated values. To take the takeoff speed, we are going to be, after we find out the distance, we're going to be timing how long it takes to get there, getting the acceleration from the thrust that we get from the motor. And we're going to basically use kinematic equations to figure out our final speed. However, we are looking into installing a GPS system to get more accurate data about our velocity. For bank angle, our receiver gives us telemetry data of that bank angle, so we are going to ensure that our plane can withstand the estimated angles. Same thing with the cruise speed is we're going to have two members stand at 100-meter distance from each other, time how long it takes, and same way with the takeoff speed measurements, it's going to be using kinematic equations, but also hope if we're able to get the GPS system, we will be using the more accurate method. And then we're also going to be timing how long it takes to do one 360-degree turn. Our second flight test, after we confirm confidence in our aircraft, we will be doing the full Mission 1, which is going to have the pilot take off, go to cruising altitude, and do the full 3 laps. So this is going to help us confirm how long it's going to take us to do the 3 laps. It's also going to confirm that the battery is sufficient enough for the full flight during flight conditions. And it's also going to see how the circuit behaves after a full flight throughout flight conditions. Our third test will be for the second mission. We will have the plane loaded up with all the cargo and passengers. The pilot will take off, fly 1 lap. After we find confidence in the plane with ensuring that the maximum takeoff weight requirements are met and it's airworthy to fly, we will then do the full 5-minute flight, attempting as many laps as possible, and we're going to confirm how many laps we can do. And we also are making sure that the plane can fit and fly with the cargo and passengers we expect. Our last flight test is going to be the Mission 3 configuration. We will have only the banner system with any weights needed to be added. The pilot will take off, and after the first turn, we'll deploy the banner. We will do 1 lap and release the banner and landing again. We will, after we validate all systems work nominally, we will then reset the plane and do a full 5-minute flight. And we're going to ensure that the system won't do an early release and will release as properly and full banner deployment, and also make sure that our test flight, our laps are.
Right. And with that being said, we are concluding our critical design review. But before that, I would like to thank a couple people. So Maddie, our mentor, Andrew from AIAA UH Executive Board, Isabella, Emma, and Gayu, Seth. Huge thanks to Dr. Thanks to Floor Corporation for the funding this year. Our alumni, Tommy, Andre, Jelisa, and Gabriel, thank you so much for being here. From MAE faculty, I'd like to thank Dr. Kelly Huang for the Wintel access, Dr. Chang and Dr. Lee for the capstone support, Dr. Chen for the laser cutting access, and Dr. Baksavan for being our faculty advisor. With that being said, thank you so much again, and we would like to take your questions.
If we could have all the FCLs.
Yes, always.
Okay, we're gonna start with questions on the people in here, and then afterwards we'll move over to the people that are online. So. Floor's open. Any questions? Start with that.
So you mentioned that one of the scoring criterion flying pace offers smaller wingspan but you need more port outs, correct, right?
More score with a smaller wingspan, yes.
Okay, so if one of your parameters would benefit you to minimize the wingspan, for one, why not a biplane design? And for two, why is the empennage so close to the main wing? Normally with a longer tail boom length, you can get away with a smaller empennage with the same color, which gets you more overall.
The empennage, it's the main wingspan that affects the scoring, not the empennage score, the empennage wingspan.
You want to take it over?
Yeah.
So you have a shorter overall fuselage length, and so the empennage is closer to the main wing. Then that usually means you need a bigger empennage because it's less of a luminar.
Yeah.
And with that, you have more drag, which means you need a longer wingspan to get the lift. To make up for that drag difference that needing to thrust something. And so by having that empennage farther away, a little bit shrunk, you reduce the drag times on the plane. You can kind of reduce the size and recover some of that score and a little bit less drag for the same lift. Why was that just a overall complexity thing where the decision was maximize the wing and just go for it?
Yeah, the general sizing of the fuselage was based on the cargo. So 14 docks and 4 pucks. And we first placed those on the fuselage and then created the fuselage around those things. And we obviously want to minimize the overall plane size as much as possible. So that's what we prioritize. But to answer why not biplane, you said?
Oh, not biplane.
Mainly because of experience within the team. We want to keep the things simple. Biplane does generate more lift, that is true. But also comes with more drag. And we were not sure about our propulsion system capabilities with overcoming that much drag with biplane. And one of the biggest design methodology or design approaches were simplicity, ease of manufacturability, and just attending competition. So we wanted to keep things simple here with monowing design.
Those are all about reasons. Because well, justify.
It's not really a question. I think that there's a lot of opportunities for low fidelity prototyping and validation for each of the design decisions that you made that just was not done until like all the way at the end. I understand obviously being in the organization for so long, we have a very long cycle of iteration, and I think it leads us to significant pitfalls like the CG not being where it should be, or like major design decisions just being not as optimized as they should be because of that long iteration cycle. And so I guess my question is, have y'all considered like doing low fidelity prototyping with like foam or to test each of the assumptions and design inputs that ended up becoming the plane as it is now? Have y'all considered doing that, or?
The main approach was a rapid manufacturability with this design, and soon test like after manufactured prototype, the plan was to start testing, and then would have some time to implement those changes. So that's what we prioritized. But again, some unexpected things such as manufacturing lab space, just us not having the access.
That's a perfect reason, by the way.
Delayed.
Yeah. Our plans got heavily delayed.
Yeah.
So one thing I was curious about in the aerodynamic stuff was how are you verifying the stability data in ANSYS and 5? You said that you got it from exit point 5, you got the stability from that, and you were planning to compare that with ANSYS. What stability stuff are you expecting to?
So there's certain derivatives and as shown in the slide on lateral and longitudinal modes that XFLAR gives us. Problem with XFLAR is that the code that it was written in isn't accurate, right? So then we have to use another software to verify that and see if XFLR even gives us valid data.
Okay, so you just want to do a test to see what lines up and make sure things are lining up so that you can kind of do it.
And also we're still learning stability analysis.
I mean, that's probably what you got.
It's worth like 3 reports.
Yeah, hang on.
Where were the equations for empennage sizing derived from? I didn't see any references.
Yes, it comes from basically in all aerodynamics textbooks, aircraft design textbooks, but we got that one from I believe Introduction to Aircraft Design by Raymer. And also I looked at John Anderson's Introduction to Aircraft Design. Same formula, same charts. Also, we really did research into winning design reports from other teams, and all teams just use this formula and with the similar coefficients.
Okay,
And that's it.
that's
Yes. Yeah.
that's a great read.
Yes.
Just wish I saw the citations on the slide.
Yes.
Follow up all of that. You guys mentioned the change to the tail volume coefficient method. Why? How is it better? What changed to get you versus the previous method? If you went with the previous method, would you have ended up with the same notch size parameters or really different? If so, how was it?
Using the previous ones, they're like slightly bigger or slightly smaller. The whole reason for using it is that it's supposedly the most optimized size.
So
Or what?
Well, for wing, it would be lift, and then for empennage, it would be stability relative to the size of.
I question what building with the top cap.
The tail boom link was. It's related to the moment arm. The moment arm data was given to me by. Which was 30 inches for the horizontal and.
You want to go into the vertical statement?
vertical, yeah.
So here. Wanted to look at the rank for this. Okay, you're good. Let's try this.
So these formulas do take into account of the tail arm, which again, obviously, as we move the wings and empennage closer together, you need a bigger surface area to stabilize the airplane. So this does take that into account. Also the wingspan and wing area. Yes. Yeah.
That's
which yeah.
I'm glad you guys are using equations formulas based off research and the size of stuff.
Yes. The LVT and the LVA, that's the LVT and the LHT, that's the distance.
No, that's good.
Was that something that you guys analyzed the effect of changing it, or was that something you're given to use fixed parameter to more parameter?
It is a fixed parameter. There it is recommended by the textbook. So there's a range of values that we can take. We looked at other teams, they just use a value something in the middle. But it's given. The CVT and CVHT.
So there's a point where you got to Aero tests, and should the Aero test, I assume the rest is all test flights. Or
Yes.
flights.
Yes.
Because it was just.
It was ground tests.
Yeah. Obviously, as you guys get our experience, get the more resources, there's a lot more tests that can be done for.
Yeah.
In that case, I just put a note about sacrificing lifts. Wherever you guys do sacrifice the lift and need to fly faster, you guys are gonna find that out when you fly it, of course, but just I'm sure it's on you guys' mind of you have to fly faster, therefore your battery's gonna die faster.
Mhm.
It's likely it might die in flight, but you might have to determine your number of laps based off how long your battery lasts. That's how a lot of teams end up doing it. It's
Yeah.
batteries die.
Right.
Um, and then also for landing and takeoff, is there a takeoff distance, distance of the game?
Nope, we have unlimited runway.
Just the run.
Yeah, just the
Of course,
runway.
You
Yeah,
don't
no
want
fun.
the whole runway, but okay, that's fine. Just making sure it's game factor. Uh, Well, good how y'all read them.
I can clarify one thing before, sorry. You said going faster drains battery quicker, obviously. We are able to account for that and calculate that in the mount app apps that we developed. And so velocity is optimized with that in mind.
And we're also gonna be bringing to competition multiple batteries. So if we do end up fully draining one battery, we have a backup for the next mission, next time we fly.
Yeah, that's fine. It's just making sure you don't. Drain faster than you expect during a flight while it's midair. That you gotta do like this. A lot of these planes fly like bricks that the. So bad for flight ratios. I like the tail section. I like how it overall is nice and simple with the box structure. Very good on that. Being able to actually complete it at this date instead of a lot later. So, I was just curious about that second spar. So there's the main spar and then there's a secondary spar that's behind it, on that second third of the wing. Why does it go all the way through? Is that just something where you have the spar and that was length? Or, was there a reason why it just doesn't go all the way?
In the main wing?
Yes,
Yes.
so this spar was basically left over essentially, but it greatly helps with A placement and B some level of switch wing box.
Yeah.
So it just the size we had, so it was actually incorporated into the design.
Yeah, I had a feeling it was one that you had left over. Yes, that's recognized it. I think that's like a 6-year-old spar now at this point, probably. Yeah. It's a good look chart. The vertical stabilizer, so I was just kind of taking note that it seems a little small, but you have a lot of control. There's the control surface big, so.
It is kind of oversized because especially for vertical stabilizer, we wanted more yaw authority, considering banner mission. So especially rudder and vertical stabilizer were a little oversized. But again, the gusts in the
That's what I put a note down that
yeah,
it kind of looked like that, but that's just based off the vibes.
Yeah, that's also
You guys did
another
your
reason.
analysis, so as
Yeah.
long as it's doing that, you do your flight test, that's good, then
yeah.
that's all.
Well, up here, you guys mentioned about the control surfaces. You have these numbers for the size of control surfaces, but not how they were obtained. You mentioned one of them maximize control authority. Is maximizing control authority really the goal here? Do you need all that control authority? Can you even use all of it? What happens if you deflect one of your control surfaces to the maximum and now it'll stall out? Is that really the best?
So the sizing of the control surfaces was, the sizes you saw were based more on the ratios themselves. To optimize them, we need to finish the stability run, which we're still figuring out. So, yeah.
When you apply it, it's for the horizontal stabilizer and the vertical stabilizer, you will see when you apply it. I try to do a turn and you'll see that you can't turn any farther. When you get that, you can see how much you're in the how far you're in the you'll find out like, certain timing and in the end,
I'm also gonna factor in how you connect the servos to all services, because you can change, like explain, it's limit or increase the travel range. Or less total.
Yes.
That being the servo.
Mhm.
From the linkage. One more point, so you can mess with the geometry to get more or less. On a bit, you push more or less toward. Yeah, make sure you don't stall those servos. I put a note way later for avionics stuff. About making sure that these batteries aren't, or sorry, all these servos aren't draining that small battery. I took a note of that, but you guys mentioned later on in part of your test was running you'll do your motor test with the battery drainage, but just make sure we're doing a full flight with multiple servos going, that the battery can handle it, and then while you're flying the planes with the road under load, 15 seconds. Holiday. And you have the ailerons, elevators, road takeoff, and all of that, it came to the and try to unlatch the banner, just making sure that it doesn't, you know, knock up. So
I do have a suggestion to that. If you're able to put a capacitor that can help stop any power spikes you might see during like hard turns. I mean, it won't help under like a constant power load, but you might see some spikes like that may help out. Yeah.
Also, you guys are using the servo range extenders. Is there any concern for those limiting the amount of current you can supply to some of these servos, especially those servo range extenders on any of the larger control surfaces?
So we are mainly using the range extenders for the banner systems because we do need full 180-degree range for the both deployment and release mechanisms. We tested both of them with the extenders and both of them work just fine. The problem with the servo extenders are they are really hard to find and purchase. So we have enough for the banner, but we don't have enough for the all control surfaces. So that's also something we're looking for.
For testing. So you talked about testing to ensure that the nose is strong, the nose structure is strong enough to hold the force from the propeller, right? But you mentioned torsional testing. How are you planning to do that? 'Cause you're very clear on how you can do tension, but do you have an idea how you would test the force?
We would attach a bar in front and just apply load.
Okay, but if you do that, how are you going to load your airplane? Support your airplane?
We haven't fully planned out the torsional test,
Yeah.
but the overall idea is having a bar and adding basically a moment.
Another thing we could just do is just run the motor on it. I would just
Or
run
run the motor and hold the plane back.
You guys mentioned just pulling forward with thrust and then also torsional for the torque of the motor. There's also bending moment applied. When you land, there's going to be a lot of bending moment from the weight of the motor. How are you testing that? Also, every time the plane has a pitch or a yaw authority, where it either pitches up, down, or yaws left, right, that motor has a lot of moment of inertia. It's going to want to gyroscopically process. That's going to apply a torque to, which might be significant. So you can do some math on that. Because it's basically going to want to twist the whole motor off.
You kind of see some twisting here.
Which we actually did reinforce that area with some possibilities.
During HAMFest, we talked to someone who builds like a lot of model RC planes. He like flew them at like Johnson like RC. Yeah, and his name was like David Dale, and he gave us a lot of feedback on how to mitigate that torsion, adding triangles on the corners to ensure proper load pathing. So we're gonna do a test and add.
Can also speeds or anything that can also help.
Yes. So we are planning to, yes.
That helped us.
We are only planning to apply on the bleeding edge and that area you just showed.
Keep going.
Yeah.
Okay. Go down a whole rabbit hole there. It's sure. The skeletonization is good overall. I'm happy with how the system got last week. You finished design issue. I will get to that. I'll get to that for like, I don't know, discussion rather than just questions, is because it's like, can I go here for shelter? Sure. Go ahead.
How are you guys gonna skeletonize this? What's your goal? How much weight are you removing? How are you analyzing it? How much? Because you guys mentioned that you're gonna skeletonize it more. How much more? How are you determining how much more?
Or was that just from PDR to now? That's from PDR. That's from PDR, okay.
Yeah.
Yes.
So
So
that's
that-
that,
yeah.
and then
Yeah.
from MV-1, we're gonna try different things like just on the side copy right here.
Yeah.
See how much weight that reduces, and then also the small things and distribute them.
How are you determining the amount?
So far, I believe we determined it by the excess space in the conflict.
Oh, so when you say removing bulkheads, you just mean shorter.
Shortening it, yes, yes. Shortening the entire fuselage.
Here it's gonna be like 2 inches. Are we gonna move this one?
Because we're gonna make it fit.
Because we don't need. We
I
don't
thought
need
you
all
were
this.
talking about removing the bulkhead, as in just removing it. As a change.
No,
we're gonna see the. Are you gonna shift it?
I had just thought that, but I haven't introduced it.
Yeah, it's, you gotta figure out.
I don't know.
Yeah. Are you considering skeletonizing it anymore or trying to remove weight on it?
Some of the, we're not sure yet, but
Because
the wings
are
yeah, the wings are gonna be made a lot lighter and off the wood. But we're also gonna take a the internal structure of the wings to not only make them stronger, but also lighter. They also need to be researched, this is for an user, but you need to prep for model elements, so.
Yeah, you might as well get.
Oh, that's not, it's not.
Yeah, you
These are detectations they served up here, sharp corners, round those off, that's not costing much of swim these terms on me, so it'll help a lot with that.
Yes. Some of them are rounded, like the internal bits and the first back.
I would say the round these off four ways right now, basically I would look at some of these.
I love 17. Watch it and then yeah, we can have some wondering out. That's what I said. Let's hold all my functions first. That's what I was trying to point out to see. Did you have explicit? Okay, let's move over to the next question. Let's go to the next question.
A comment, love the page of formation sensitivity analysis. Question on the Velcro. It is allowed rules.
Yes, yes.
Oh, good.
It is good on rules, yes.
On that, I saw that you already had a problem with it. I was gonna make a note of it, and then I saw it. When you are trying to fit things in and move them to the side and slide parts on top of each other, you can't slide it. It's just a little.
So,
so sorry. So lift it up higher.
Yeah, I just meant the difficulty wise.
Yeah, that's what
we are planning, so how the intended, I guess, I'm not quite sure how to say the word, but how the procedure, the intended procedure is, so right now it's currently with these screws are unfinished, but there will be a flat surface here, so you can slide it on top, so you're not touching the Velcro and then smack it down.
Yeah.
Or not smack it, or place it on the, so you have, because there's a whole 2-finger space here, so you can just slide it up top, do it, same here.
Well, thank you sure you get the.
It's like cargo. So like excellent. Yes. Yes.
So this is the entire.
Just, well, that's just.
Out here.
Yeah, the requirements require the ducts to be isolated.
And then.
So it's not question. Oh, yeah. You know what?
I believe, yes, so then we will tour and have it all. Yes. How much is that? CG, why this is all, thoughts back?
So it's kind of far back. Loaded.
So this is fine.
We're trying
The rear acting or those.
Okay, yeah.
We are producing weight for our RCG pages.
Unless that's.
Yeah, almost. But we're gonna have.
That's approval of the mission of the weight difference by mission. But no associated CG, and the weight difference was about was little the place check, so I'm assuming. That there's some significant effect.
So
Weight difference shows-
CG, when you have the 40%, how far is C?
So first mission is further back. When we have all the weight on it, it's actually going forward. So I think we had it where the payload was in there. So it unloaded.
I would just make sure that your CL versus CG is somewhere where the plane is still stable for any operating conditions. Even if, for example, let's say you did your math, or hey, it'll work if it's fully loaded. What happens if you get to comp and you determine, oh, we can't fly this fully loaded? You need to fly it with half payload. Is it still gonna be okay? Is the CG still acceptable?
They allow ballast at completion. We also have a range for allowable CG. It was, I believe, from 15% of the mean aerodynamic board, measured from leading edge to around 30% to 5%. That's what we're aiming for, but the best stability is achieved at around 25-20% range. So on the spark, as Carson said, if it's not on the spark by the flights test, we are not going to even try to fly plane.
Which we're still looking into the ballast method and what experience is ballast material and the tech methods, and that is still part of being looked into.
Is that ballast method for MV-0 only?
Yes.
As in, if you have enough time to make it in MV-1, then you would be adjusting the path.
MV-1, most of the ballast should most of the ballast should be already the payload, and then possibly adding. Like we haven't looked fully into it, possibly adding smaller ballast, because by MV-1 we should know what ballast where things in, and it should be a systematic ballast, I suppose. So it would be big. Plus also the wing could be moved further back, so one stuff's going to be front. So the CG is not going to move vacant. The CD will naturally move.
How about it?
Yeah, I remember being like, you gotta move it back.
Yeah,
So it's already moved, but
So, yeah, so.
That also leading to the other question that I had was that if the difference in CG by mission is significant enough, would you consider doing a sort of removal or adjustment of valves for the final phase?
Yes, yeah. Like the preset, or not preset, but based on mission requirements. Yeah, we would test out what ballast is needed for each mission, and we are allowed to by the rules.
That's what I was.
Yeah, we are allowed to by the rules to have a ballast at, like for example, for mission 1, we could put the same weights as the bucks and the ducks would weigh, and basically fly as if there was a ducks and bucks.
It's just wait, that doesn't. And for competition, you have to mark where the CG is for each mission, right?
Yeah.
So.
Be wise to do that either way. We weren't required or we were.
For the landing gear brackets, I would just recommend threaded inserts. So when you tighten it down, it's going to the threaded inserts and not in plastic or a nut that goes on the other side.
Oh, no, the back landing gear? No, that one, you don't have to.
Sure, landing gear.
Is the front one on there? Is that the
Yeah.
first?
Partial, that's the first. It has the on the.
already did the set of testing.
So, what filter is that?
It's 40% gyro full. Oh, yeah, like,
You can peel it.
You can play with how much.
Yeah, plus.
It's
It's what we have very available, and it's a lot better than this. Okay.
That's.
Not very much.
Why specifically PLA? Is PLA is generally a fairly brittle material. Landing gear is something that is going to be subject to a lot of stuff.
So this PLA plus is a lot more tougher than normal PLA, and I know there's a lot of impact force, and then it's also gonna have the first complete bulkhead is very good. And we also want to test it with the
a breaker or won't break.
Yeah, that's what
We actually did test.
not-
That's right there.
That's not partial test.
It's like 10 kilogram load, which is 100 newtons, and it was proof of concept. But
test that.
for that,
In terms of a load pack within.
Yeah, that's what we're gonna do now.
A lot of landing gear. Oh, this one's all. So the plan, we have two levels of rear and behind gear. For the rear landing gear, they're steel, like steel, not wires, but steel bars, like things you bars. Yeah, but it's near venture. But the front, the plan for MV-1, there's my plan for my head. skills yet to be introduced, because you have no testing when you enter, is to add a larger piece that incorporates bulkheads and will give you the linear, yeah, it's not. Yeah, it's going to insert, so, well, that's a big experience. If you haven't played around with this yet, you can make the overall shape that you want to cover all the surface area bouncing points that you want. And then messing with the, so you can have these minor infill, where you want those low pass pretty consistent and strong, you can use, the
Localized
modifiers, like, you know how you can add a negative volume for, you can add a part, you just add a box or a sticker. You can do the modifiers where you can make that 100% infill. And so you can have where the screws are going into, that's 100% infill, or has wall thickness of like 5 walls.
That's close.
And so that way you can have those walls.
That's it.
So you can have
single areas that are stronger and then leave the rest of the spin.
So it's not, you have to have that like this thing. It's side shape and door. But how most of the structure be like 10%. When you get into surface, you want to advance 10%. I would say you have to be fully space.
Like when you're like at the Airbnb, every time before you go to come, like shut down.
Items to bring there?
Items to bring, but also like requirements for the plans. Because you'll do tech inspection, you can pass it. Something might happen to where you need to change the plans.
Yeah. We are bringing a toolkit. Let's check this. Yeah. Trying best with the.
Like,
If I could say,
for instance,
we are
checking the CG.
discussing, yeah,
Always check the CG.
yeah.
The reason we crashed was because we modified the client, did not check the CG. That's what we're good.
Focus on the questions right now, then we'll go in. Time here, I wanna get to all the questions first. We love having this discussion, oh, we can talk about this all day, but.
I have a question. So have you thought about maybe changing out the types of wheels you use to maybe get some of that impact force distributed a little better, or maybe like a rubber wheel that may be elastic that can take some of that impact out? You can change out the wheels. With the question. Yeah, that's right.
like squishy wheels.
So we got like rubber wheel. There's some that I have.
Leave a footnote. Yeah, so further, but no, first, we have not really looked at something else.
Yeah. Yeah, let's read it here. Let's read the.
Let's get to it. It's
Chat, from Katie. In terms of power consumption and stability analysis, has the team considered using dihedral wings? Any benefit for this in the 3 missions? The wing allows flight control with only the empennage and also gives you rolls stability. All right, so we did look into dihedrals, but due to our lack of experience in manufacturing dihedral, we decided to keep it with a straight wing with no dihedral. So we did look into it, but we want to keep things simple. So we just kept it simple. We did not feel confident enough in our abilities to manufacture a proper dihedral. And then yeah, that was.
I have a follow-up question on the same vein, as the. So you guys are saying PLA plus because it's what we had, not acceptable. You guys know me. I have a global filament. Not acceptable answer, not at all. Would you imagine everything?
Yes. What filament would you recommend? Like genuinely, what filament would you recommend for this?
There's no reason that it needs to be a rigid filament like PLA that is going to brittle failure. Look at exactly what the people in like the small weight class of battle bots use for FEM. They're printing stuff out of like TPU. It deals with shock rate.
Okay.
Right? Because TPU is never going to shatter. It's just going to bend a little bit. Here it has some stiff TPU. Bending is fine.
Well, they
prefer it. Yeah. So there's no reason to make something there refused. Yeah.
Yeah. Well,
also, you guys mentioned a lot of what was PET GCF. Where is it on this plane? And these end plates basically important. Yeah.
And the
You're gonna hear me saying a lot. Why? Why is it that we see us?
And then these guys start with theirs.
It's what we had in inventory, and we did. Yeah, that was correct. And it's not the real answer, but it is the honest. You don't have to work. You don't have to write it. Right.
I'll tell you guys right now, whenever you're working with FDM, for instance, any kind of thing that is whatever carbon fiber, whatever glass fiber, throw it away for this purpose. It's not useful. All the filaments do is increase its thickness. However, you're going to reduce the interlayer bonding as well as actually just absolute strength, because having that glass fiber or carbon fiber in there just reduces the amount of filament bonding. It's weaker. It will nail at a lower load, but it's stiffer. For your purposes, not useful. It just adds cost, adds weight. Also, even if this is just regular PETG, so I don't cook you on it being carbon fiber, why PETG? It's heavy. Does it need it? Why not a lightweight film? I've worked those before. The plane from my year has a lightweight PLA like empennage centerpiece. All the load path for that entire empennage goes through lightweight PLAs that is sanded so thin that you can see through. Why do these need to be solid PETG?
They simply don't need to be, and this is something we're considering for the final aircraft. Ideally, single rib structure. So if that's the case, we don't even need to 3D print. That would be single wood rib. Ideally, again, for the control surfaces, we 3D printed them because of the design, but we would like to do foam cut for them. For like the if it's hard, you know, there are methods like you explain me. So main reason with those thick ribs were the taper. It was just easier to 3D print, and it was the material we had with us. So that's why we did. But
MV-1 material we had is not an excuse anymore.
Yes.
Ask me, please.
You know, and for MV-1, like, if we're gonna be using,
Yes, you switched a little bit. I really do. I have a garage space that is.
I would.
Are you putting? Yes, you have a full surface. Yes.
Yeah, I would like to mention, this is kind of for so the 3D printing, yeah, it could be like this, it could be lighter.
no, yeah,
It's like we're gonna switch.
it'll be full.
The main reason we're gonna do both because we need to, one, we're gonna have some. Yeah.
Yeah.
Things. Let's get around. Get it where it's
Still saying next to
also-
my.
So this is one of two. So I think. If you look at this, the only we need now we are shocked to we talked to David Bauer, which was people who. We a lot about special. Yeah, we're discussing again. Yeah. I work on a question. We'll talk.
Questions after question.
Alright, next question. So there's a thing on the banner, banner past 25 inches. Being something that was noted. Can it not do that yet? Because you guys have the really long banner. So they try to make sure.
That was the initial goal.
Initial goal, and
Yeah.
now you guys have determined.
Yes.
It's not even, I wasn't sure if it was
Yeah.
something that. It was part of your plans to find out if you can fly a plane with 25 inches, it's stable, then move up. That was already,
Mhm.
that was.
I got a follow-up question on the banner. Do you have any kind of plan or procedure for fixing it if something goes wrong, competition, like it gets damaged?
You got a backup? Yeah.
You're not allowed to fix them, I believe, for the rules, correct?
So from my understanding of the rules, you're allowed to enter 2 banners, but you have to fix them before attempting a next takeoff if you have
If they break, you can fix them, but you have to resubmit them to tech inspection.
Okay.
Yeah.
It's a second inspection. Because you modified. So, does the banner system, deployment system have to be in other parts of the rules that say that it has to be within the aircraft, or can it be externally mounted? Because I know that the loop portion is externally mounted. Is there a rule saying that it can't be?
So only banner itself has to be sold externally. The banner system, the deployment mechanism, release mechanism can be internal to the aircraft.
Okay, I guess just reverse that. Is it not allowed to have some of the banner mechanisms outside here?
Like. So you.
Would this be allowed outside of the aircraft, having this as own views? Not allowed?
Yes, you're not allowed to store the banner inside
The banner's the only thing that has a placement, which is the banner.
I
So
will
this,
double check, but I mean, this is, I was gonna make sure they're saying it without this.
Yeah.
You know, we just see everything we can. Comment about a lot of this, you'll find out from this on market. You're gonna start to like wrap it, or like here, it's like, how am I gonna work, how are you gonna wrap it?
Well, for those area, nose cone and back area, we are planning to use the thin balsa, 1/32 inches. Like,
Oh, you're right, then.
Like short foam, yeah.
Foam inserts and pinballs. I mean, yeah, again, that's from experience, my first version was almost like this, and then I updated it, and it was a lot different.
Yeah.
And
Quick question on the banner deployment. So this here is what's holding your banner in, right? That little ring there. Have you tested to make sure that this thing is still gonna be able to release the banner when it's under actual area, right?
We're going to test it soon. So we'll go, first test, we're gonna attach a 3 pound weight and drop it 20 times, and then we're gonna cut. And then we're gonna put it, I guess, just the first side. We're gonna try it in the wind tunnel and just have it.
I would definitely test that.
We're definitely gonna have
I would have concerns about that little tube ring digging in during flight.
Yeah.
I mean, moving around for turbulence. If it digs in the wrong way into that plastic there on that rack and jams in place, you're not gonna be able to release it. So.
where's the tow line? The
bars are, well, it's.
You wanna pick over the banner?
Oh, we can grab it. Sure.
Yeah, so. So what? So release this to release.
Yeah, then it's to release it.
To release the banners. Oh, so the banner being towed from.
Yeah. That's where.
Yeah, make sure those are good.
Yeah, we're definitely testing it, you know.
I'm sure.
And the banner has to be deployed and then released.
We're planning for.
Or
Yeah.
Yes.
Yes. So on top of that, already the 50 pound line, oh. Have you guys got the load from your testing? Did you get how much load is expected from that banner?
Yeah, we're shooting for a max of 10 newtons, so it's just for overkill, but
That was it, just that's actually.
From here. This is what this is your. Force 80 pound.
Yeah, I'll say, I'm just making sure, like, you know, this, that, I know it's not gonna be 50 pounds, because that, this doesn't produce power, rest, but I'm just curious what your.
Hey, motor KV. You guys have like 210 kV. And got that off the 370 kV, right? Yeah. So you guys mentioned that it gives you was it less the maximum amperage the motor can sustain. That makes sense. Higher kV can sustain more amps. However, a lower kV motor will give you more torque per amp. So that motor should be able to sustain a lot higher peak torque than a 370 would, which means you can probably make up for a lot of the difference from the 210 to 370 that you're expecting by going for a more aggressive pitch prompt. Have you considered that?
No, we have not considered that. That is true, but lower kV motors are rated for higher or higher load cell, or not load cell, but S-type battery. So we would need a higher capacity and performance battery, which we don't currently have, and we looked into those kind of batteries. They are expensive and very heavy.
Also, they would break.
Yeah,
the maximum.
Exceed the maximum.
1 hour. They're even for this current battery choice, right? It literally gets right on.
99.9. Yeah.
One thing you can, you guys mentioned, for example, in finding that 370 kV motor. The only difference in motors kV is the gauge on the wire used to wind the motor. A lot of people that run RC hobby shops will have experience doing custom wound motors. Particularly, a lot of guys that do high-end FPV drone racing, they will often take a motor, strip it entirely, and rewind it themselves. You may be able to ask one of those guys about winding that into a 370 kV.
And does that violate rules modifying motors?
Is there anything about motors on there? Never seen.
We'll have to check. You'll have to double check.
It might be something, it also might be something they can't verify. That
it will be that.
They would be able to verify if they see suspicious motor and power draw, they will look into it. That's happened before.
Yeah.
100%, it has happened before.
I know the battery.
Yes, that's what I was saying.
Oh,
No modification battery.
Oh, I accidentally Oh,
That was me.
that was you? Okay.
He didn't say it's 370.
Oh, is there any more questions online?
There's one more question online, yes. On the banner mechanism too, the rack and pinning comes with challenges of bump and stickiness. Has this been evaluated for the system? And I believe you actually asked that question.
That's, I think it sounds like a different.
That sounds like a slightly different, yeah. The stickiness, right, yeah.
Yeah.
There's a bump and stickiness. Has that been?
Actually pin getting bound up by being pulled.
I think that is the same question.
No, they're
No, it's slightly,
Is it
it's
not?
different.
Potential cause, same end result.
Same end result, yeah. Has that been?
If you want to answer it, I guess.
Same answer. We're gonna test it with a 3-pound weight, and then we're also gonna test it in the wind tunnel with the banner fully deployed.
And the ultimate testing will be the flight test. But so far, everything works in isolation. But again, it requires some tests.
I have a question that just came up now. If for some reason you cannot release the banner while flying, is that going to lead to severe problems while trying to land the plane? If you're doing like your test flight and the banner does not release, does that mean, yeah, this plane is crashing?
We can't for sure tell if it's crashing, but it will be a hard landing. Hard to land. Given the for final approach and flare parts, the banner will be dragging on the runway.
It is, and imagine, like, we would be disqualified for that run, we would have to run, do it again. Basically, that run will be,
If you
We are
if you link that.
if we get the plane back, yeah.
Like test flight,
Yeah.
or even just like, oh, your plane is like dead now, there is no run to because.
Because like, see if you can land the plane. Because
We,
At least either that or intentionally design in a weak link on that banner mount.
I assume with that, y'all are assuming like, oh, it doesn't release and then we're landing in it, let's say it catches us something, makes back, flies back and do another run. You don't want a weak point possibly somewhere in the bar here. That if it catches on something, it's not. Now we have 2 halves of a plane, not a full plane. Now instead it's just, oh no, we're out of range.
Yeah, or if it sticks in the ground and then it torques the
Yes,
plane
exactly.
inside a weird end.
Exactly.
Just something to consider.
yeah, and with testing that, it's a bit of a risky test, especially due to our time constraint.